Hey friends, welcome back. I have a problem. Something that my calorimeter can't really solve for me. Now, I have a situation in which I want this reaction right here. This reaction for the production of sulfur trioxide. Don't worry why, it's none of your business, okay? Anyway, every time I do the reaction though, I get a mixture of things other than sulfur trioxide, like sulfur dioxide. So, how can I know what my enthalpy will be if I have a mixture of things and can't isolate the one thing I want? Oh, it's so frustrating. But there is a way to solve this. So, stick around and we'll figure this out together. Here's how we're going to solve this. It's through something that we call Hess's law. Hess's law. And it works like this. If you don't know the thermochemical equation, then you can use other thermochemical equations to accomplish what you need. You can add enthalpy changes, delta H values, of known thermochemical equations to find the enthalpy change of a final unknown reaction. So let's try that with the one that I need. Okay, I found some building blocks that I can use. I found two thermochemical equations that have some of the same ingredients as the equation I'm looking for. Just to remind you, our top equation is the one that's unknown. 2 moles of sulfur combined with 3 moles of oxygen to give us 2 moles of sulfur trioxide. That's the enthalpy change we're looking for. But we don't have that. We do, however, have these. Sulfur, 1 mole of sulfur combines with 1 mole of oxygen to produce 1 mole of sulfur dioxide. It has an enthalpy change of negative 297 kilojoules. It's exothermic. Now, I also found this one. 2 moles of sulfur trioxide, our product, right, will decompose to form 2 moles of sulfur dioxide and 1 mole of oxygen. It has an enthalpy change of 198 kilojoules. It's endothermic. But how do I use these to get to this final one right here? It's going to take a little bit of changing around. So watch this. Now, I notice that in my desired equation, I have 2 moles of sulfur that I need. And in this reaction, there's only 1 mole of sulfur. So what I'm going to do is I'm going to multiply this entire reaction by 2. That way I'll have 2 moles of sulfur to match my equation here. The thing is, if I do that, I also have to multiply this by 2. And so that's what I'll do. Again, because I needed 2 moles of sulfur for my final reaction, I multiplied the enthalpy change, which was negative 297, and now, since I have 2 moles of sulfur, that becomes negative 594, twice 297. Now for this bottom equation, I notice that my sulfur trioxide is a reactant, not a product like I need it. So I need to flip this around in some way so that sulfur trioxide will be a product. That's exactly what I'm going to do. I'm going to turn this around and make this the reverse reaction. But in doing so, I also need to reverse the sign on my enthalpy change, like so. So I'll make the change and you'll see the result. Now that's a little better. Notice that my sulfur trioxide is now a product, like it should be for the reaction I'm looking for. Now what we'll do is we'll add these two equations together. We'll add all the reactants together and add all the products together and see what we get. We'll also add the enthalpy changes together as well. One thing I wanted to show you is that when we add these two reactions together, here's what we get. 2 moles of sulfur plus 2 moles of sulfur dioxide plus 2 and 1, 3 moles of oxygen yields 2 moles of sulfur dioxide and 2 moles of sulfur trioxide. You might be thinking, we've got extra though. We've got extra things in there. That's not the same as what we have up top. But watch. Notice that we have 2 moles of sulfur dioxide on both sides. That means they cancel each other out. So when we cancel those things out, we're left with 2 moles of sulfur and 3 moles of oxygen that yields 2 moles of sulfur trioxide. We add our enthalpies together and we get a total of negative 792 kilojoules. So that is our enthalpy change for our reaction. So there you go. We used Hess's law to be able to determine the enthalpy change in an unknown reaction based on 2 other reactions that were given to us. And that's the way it's going to work on a test, by the way. You would be given reactions to try to solve for an unknown reaction. And you'll have to rearrange those, maybe turn them around, maybe multiply them by a certain number in order to get what you want. But the result is that you can simply add together the enthalpies and get the total enthalpy change. Hope that helps. Can you imagine, though, trying to find the enthalpy changes for every reaction in the known universe? It would be crazy and maddening. But there's a way that scientists do this. Instead of doing all that, what they do is they find what we call standard heats of formation, the amount of energy required to form a particular substance. So in the case of our sulfur trioxide, we found that this reaction had a delta H of negative 792 kilojoules. So if I just want the energy for 1 mole of sulfur trioxide, I simply multiply this whole equation by 1/2. And I multiply the energy, the enthalpy required, by 1/2 as well. So I get my 1 mole of SO3, and by the way, it's okay that we use fractions here. And I find that I get an energy of negative 396 kilojoules. This is what I call my standard enthalpy or heat of formation. In this case, the energy that it takes to form 1 mole of sulfur trioxide. But you might be asking, well, wait a minute. How do we know that all that energy is from sulfur trioxide? What about these guys? What's their energy? Here's the thing. For any element in its standard state, the energy is 0. It doesn't take any energy to be at that state, does it? It only takes energy to form things or to break things apart. So because of that, sulfur, solid, that's its standard state. Oxygen, gas, that's its standard state. So both the energies, both the enthalpies of formation for these two are 0. That means that all this energy is locked up inside of sulfur trioxide. So just so we're clear on this, elements in their standard state, in the state that they are normally found, well, that's sort of like a starting point for our energy, going up or down from there. So sulfur in its solid form, that requires no energy really. That's the way it normally is. So its enthalpy, its heat of formation, would be 0 kilojoules. And likewise, oxygen is normally in a gaseous state, isn't it? So that requires no energy to become gas. It already is gas. Its heat of formation would be 0 as well. Just to make sure we're clear, elements in their standard states have an enthalpy of formation of 0. So there's another way we can actually use these heats of formation to solve for the heat of a reaction, the standard heat of a reaction. That is, this is a sigma, by the way. It means the sum of, to add them all together. The sum of the heats of formation of the products multiplied by their respective coefficients, you'll see what I mean, minus the sum of the heats of formation of the reactants multiplied by their coefficients. So let's do an example to make this clear. So here's a reaction of methane gas combusting in oxygen to form carbon dioxide and water. We have some known heats of formation for these substances. For example, the heat of formation of carbon dioxide is negative 394 kilojoules. The heat of formation of water is negative 286 kilojoules. The heat of formation of methane, negative 75 kilojoules. What's that? You said I forgot one? Did I? Did I really forget one? Come on, guys. What's the heat of formation of oxygen in its normal state? Element in its normal state? It's like I just said it. That's right, 0. So now let's use these values and arrange them in such a way as to solve for the heat of reaction. Here we go. Okay, so we're going to use this equation right here to solve. The heat of the reaction is equal to the heat of formation of carbon dioxide times 1 plus the heat of formation of water times 2. Remember to use the coefficient. So we use the coefficient right here. We'll multiply water's value times 2. So that's our product section minus the reactant. The heat of formation of methane times 1, right? Plus the heat of formation of oxygen times 2. Now, one good thing is we can already do away with this because, after all, the heat of formation of oxygen is 0. Now we just need to fill in the values. All right, so filling in the values gives us the heat of reaction equal to the sum of the products, negative 394 kilojoules for carbon dioxide, negative 286 kilojoules for water, times 2, because water has, there it is, water has a coefficient of 2, minus negative 75 kilojoules for methane, and plus 2 times 0. There's nothing for oxygen. We simplify and we get negative 394 minus 572. That's our products, minus 75 kilojoules. So negative 966 kilojoules plus, right, negative of a negative, plus 75 kilojoules gives us negative 891 kilojoules for our heat of reaction. Got it? Okay, I want you to try 2 problems this time. You can do it. I know you can. Here's the first one. If I have this reaction, ammonia, 4 moles of ammonia gas combines with 7 moles of elemental oxygen gas to give us 4 moles of nitrogen dioxide gas and 6 moles of liquid water. What is the heat of the reaction? And here are your known heats of formation values. Okay? All right? That's the first problem. One more. For this one, you need to use Hess's law. We have a reaction with an unknown enthalpy. And I've given you 2 known reactions. This reaction, the reaction of carbon monoxide and oxygen, has a delta H of negative 566 kilojoules. This reaction, the one with nitrogen and oxygen, has an enthalpy of negative 180.6 kilojoules. So use these 2 reactions like I did with the reaction in the beginning to find this reaction. You're going to add these together in such a way, right? Rearrange them if you have to, and come up with this reaction, and then how much enthalpy do you have from it? Get it? Okay, I know you can do it. Okay guys, so it's been real, it's been fun, and yeah, I kind of think it was real fun, but maybe that's just me. That's okay. Anyway, what did we learn today? Well, we talked about Hess's law, how you can add together enthalpy changes from known thermochemical equations to come up with the enthalpy change of an unknown chemical equation. We also talked about heats of formation, how much energy it takes to form particular substances, and how we can use those substances and those heats of formation to come up with the heats of an entire reaction, the enthalpy involved in an entire reaction. Wow, what a day. I hope you learned a lot and I hope it was beneficial to you. Can you believe it? We're almost through the chapter. Just one section left. So, great job so far, guys. Keep it up. Keep up the good work. Do those problems for me. Again, I hope to see you guys really, really soon. Until then, God bless.